Welcome to the GISTP 2022, and I'm Carlos, and the MC of this judging panel. This is team from Georgia, and the project title is New Identity for Regular Tetrahedron. So first, thank you very much for your presentation and joining us for this final and your development of this science project. Thank you very much. So today we are glad to have Professor Ho from the Chinese University of Hong Kong and Professor Zhu from City University of Hong Kong to be our judges of this competition. So please note that this window will turn into a countdown timer when the judging officially starts. You have 5 minutes to present your project with screen sharing of PowerPoint or other materials. We will remind you the time after 5 minutes, and you have to stop your presentation when the time's up. Okay, so after your presentation, you will have 4 minutes for the Q&A sessions. Do you have any questions? Any problem? No. So if you're ready, please share your presentation material now.
Can you see the screen?
Yeah, sure.
Yes.
Yeah, that's clear. Thank you. If you're ready, you may start now.
Hello, I am Lia Razmadze. Salome Berita. And we have a presentation about new identity of the regular tetrahedron. Investigating three-dimensional shapes, we were interested in regular tetrahedron. With the help from our teacher, we found material regarding this at Alex Bogomolny's site, Captain.org. A site filled with numerous interesting theories in algebra, calculus, geometry, and many more. We looked through the theories in our area of interest, geometry. The geometry section was filled with 1,824 theories, and we came across and discussed theory number 157. Concerning a new identity for regular tetrahedra. Miguel Ochoa-Sanchez theory proves that the sum of the squares of the distances from the vertices of the regular tetrahedron to a point on its circumsphere is constant. To prove this theorem, Miguel Ochoa-Sanchez chose an arbitrary point P on a circumsphere and connected it to the vertices A, B, C, and D. He calculated the sums of the squares of these four distances and as a result got a constant number, 3 times L squared, where L is the side of the tetrahedron. This theory was proven using spherical coordinates. We proved the same using Cartesian system. We also proved that the sums of the fourth power of the distances are constant and the point can be on the surface of any sphere, the center of which is the same as the center of the tetrahedron. We also tried to prove similar hypotheses for the third powers, but the sum wasn't constant. We decided to check if the sum of the fourth power of the distances is constant. We did appropriate calculations and got that, indeed, the sum of the fourth powers is also constant and is 3 times as much as the fourth powers of the edge length. We continued research for more general cases for any sphere, center of which coincides with the center of the tetrahedron.
To simplify calculations, we constructed regular tetrahedron such as the center of the base lies on the origin of the coordinate system. One of the vertex lies on the x-axis, another one lies on z-axis, and the center of the tetrahedron also lies on z-axis. Based on this, we calculated the coordinates of other two vertices. Using Pythagorean theorem, we established a relationship between the radius r of a sphere marked on a regular tetrahedron and the vertex of the regular tetrahedron. We expressed coordinates of the vertex of the regular tetrahedron in terms of r calculations and introduced parameter t to generalize the case. So we get that r equals 3 times root from 2 times t, so that the coordinates would be much simpler. The coordinates using t parameter are also shown below.
We considered an arbitrary point A with coordinates x, y, and z on the sphere with the same center and different radius L. Using the formula of the distance between 2 points, we wrote the sum of the distances between the point A to the vertices of the tetrahedron and the sums of the square distances and the center of the sphere. When we simplified the obtained expression, we got that the sum of the squares does not depend on the coordinates of point A. We continued research for the sum of fourth powers of the same distances. We squared the squares of the distances and tried to simplify the sum. We got this huge expression and almost lost hope that it could be simplified, but thankfully, in the end, it simplified, and we obtained this expression, where r is the radius of the circumsphere and L is the radius of an arbitrary sphere, concentric to the circumsphere. So we formulated theorems.
Theorem number 1. The sum of the squared distances from an arbitrary point on any sphere with the center at the centroid of the regular tetrahedron to its vertices is constant and equals to that. When L equals to R, the point lies on the circumsphere, S equals to A times R squared, and R is that. And if we substitute R in formula with S, we got Sanchez theorem. Theorem number 2. The sum of the fourth powers of distances from an arbitrary point on any sphere with the center at the centroid of the regular tetrahedron to its vertices is constant and equals to that. When L equals to R, so the point lies on the circumsphere, then S equals to that, where R is that, and as we know, S is an H. And if we substitute R in formula for S, we get that the sum of the fourth powers distances equals to 3 times S to the fourth power, which was our result shown previously. Thanks for your attention.
Okay, time's out. Thank you very much for your project. So let's see if the judges have any question for you.
Thank you, team. It's a very interesting project, I would say. Although you have demonstrated some theorem, I think the tetrahedron being confined to a sphere has special properties. Am I correct? I mean,
well, technically, yes. If the sphere is concentric to the tetrahedron, it has the special property where the sums of the fourth powers of the distances from the points of vertices of the tetrahedron to any point on the sphere is constant.
Yeah. So it's a kind of extension of geometry. When the boundary condition is in a spherical shape. Now, my next question is: now you have proven what already I would imagine being proven by other mathematicians. What is the new aspect of the project?
So previously, what was proven is the sums of the squares of the distances, right. And the sphere had to be directly on the tetrahedron. Well, we proved this for any sphere concentric to the tetrahedron, and we also proved the fourth powers instead of the sphere being circumscribed on the tetrahedron. So the sphere can have any radius L, and the theory would still be correct.
You mean the other 3 vertices do not need to be at the boundary of the...
Yes.
Okay, so that's
what
actually... Sorry, so Professor Ho is okay?
Yeah, please.
Okay, good. So it's a very interesting theorem, actually. It's quite interesting. So in your theorem N1, how does it different than Sanchez theorem, which is also to the second power? So is the difference just what you just mentioned, that is that one of them in your case is a concentric to the tetrahedron, any sphere, any size, fine. But for Sanchez, you need to the vertex need to be on the the spherical surface, and that's the difference. Now
that's the difference, along with the fact that we proved the fourth powers also,
and also the fourth power. Yes. Now the next question is probably a little bit more abstract, a little bit more need to think about. What is the implication of the theorem that you just developed? How can people use this?
So we can use this theorem in math, obviously, but we can in astrology. and that's it, mainly in math.
Okay, so this is obviously you guys just start working on this is also very exciting for you already. So about derivative new theorem, but I think the next step you really you need to think about, hey, what can I do with this, right? How does I impact it? Is it possible to apply this to some kind of topology applications? Now there's a lot of topology thing that people are working on right now, right? About different topology or nanomaterial and so forth, that you position different kind of like tiny subjects, arrange them in the space to create new material, say for example, right? So think along that line as you develop, but what you have done is very, very exciting, very interesting. Thank you very much for showing it to us. Okay, best of luck with your study. Continue.
Thank you for your time.
Thank
Okay,
you.
thank you.
Thank
Bye-bye.
you, judges. Thank you, judges.
Bye.
And
Thank you.
team. So see you.
Bye-bye.
See you again in the closing and award ceremony tomorrow. Thank you. Thank you very much. You may leave this Zoom meeting room now. Thank you.